This call is going to be recorded. Not a whole lot of people on here, but I did send it out to all the mailing lists and on Facebook and all that kind of stuff. So, and it'll be recorded anyway, and so we'll be able to at least document all the different updates. Everybody's going in a bunch of different directions and stuff. So hopefully this video will kind of pull it together to kind of show what everybody's been working on, their own projects, stuff that's been going on down in Tonopah at EPD Labs, and new book update, which is finally available on Amazon and as an ebook on emediapress.com. So today is December 16th, Saturday, 2023. It's 1 o'clock Pacific Standard Time. And we have Eric Dollard on the call. We have Griffin Brock, Haka Says, Adrian Marsh from the UK. Justin Miller, who also helps out with EPD Labs, is hopefully going to be joining us with a slideshow of kind of what's been going on. Griffin sent a few bullet points on some of the topics to cover on the call. I'll just start with some general announcements, and then we can kind of go in and then talk about the book, and then we'll go into Griffin's list. Let me just get that up here on my phone real quick. Let's see, wrong project. Okay, so EPD Laboratories Inc. is a 501c3 nonprofit, and I just want to let everybody know, if you do have questions, hold them to the end. We'll just kind of go through everything, and then we'll just open up for questions, and everybody can just kind of jump in. EPD Laboratories Inc. is a 501c3 nonprofit corporation down in Nevada, and any donations are tax deductible. These funds help to keep the operation going, and this is to further the research in the electrical sciences. As you know, pretty much all of us collectively are kind of moving on that same path, and Eric's been on it a lot longer than most. This past conference, every year we've had a conference. This year was the 12th annual Energy Science and Technology Conference here in Spokane, Washington, at the shop right here that I'm sitting in here, and it happens pretty much every July, and it's started as a 3-day kind of event, and most of them have been 5-day events, Wednesday through Sunday, where there's about, I don't know, 15 to 20 presenters, presentations, demonstrations. There's a lot of super technical talks that's, just for people who kind of have a background in electrical engineering, mathematics, and that kind of thing. And then a lot of the other talks are simple enough that even the layman can understand most of the concepts kind of going on. And we like to show a lot of demos instead of just talking about, theories and ideas, but actually showing groundbreaking research in the electrical sciences, and not just electricity, but with Tesla turbines and these other kind of technologies. Everybody that you're seeing here on the screen today has presented. These presentations are on emediapress.com. If we had a conference next year in July, it'd be the 13th annual conference. So far, my plans are, I'm not really feeling that I want to do the same kind of conference yet. If something strikes me in the right way or whatever, we'll plan on doing something, whether it's either, maybe a couple day, weekend get together, some type of intensive, a workshop or whatever. I'm open to suggestions. I just need help organizing the whole thing, because when all is said and done, it's a lot of work. It's great to get the presentations together and everything, but it's just too much for me to do all that when I'm trying to put products into production, which is kind of where my focus is kind of going with the water purification technology and some of these other things. Now on Eric's website, ericpdollard.com, let me see if I can get out of here to just showing share screen. Do you all of you see all like 5 of us kind of pinned on the screen there, or do you see anything else? That is what you see? Okay. So let me see if I can, this is not letting me escape here to go to Eric's website. Oh, here we go.
All right.
Okay, I'm going to show Eric's website real quick. This highlights a lot of his work. Griffin has been kind enough to
check the share screen again.
Right here. Can y'all see Eric's website? Okay, so this is ericpdollard.com. Griffin has been kind enough to kind of share a lot of the updates and kind of keep it going. And there's a donate link right here in the main menu bar, and if you scroll down, you can donate by either a PayPal, or if you send a check or money order, that'll come to Spokane. I just endorse those checks and send them down to the bank in Nevada. That helps to pay the bills and kind of keep these projects going. Also, pretty much everybody on this call. Let's see, stop share. Been a little bit since I've used this Zoom, but on Adrian's website, am-innovations.com, griffingBrock.com. Haka says, what's your website? I don't know if you have anything.
It's hakasays.com. Yeah.
Hakasays.com. And so at least I know Adrian and Griffin's site also has a donate link. And if anybody wants to send funds in their direction, probably PayPal is the easiest. That helps to go into these projects that a lot of us are, openly sharing everything with you. So any kind of contributions definitely help. Most recently, Eric is always writing filling up notebooks, notebook after notebook after notebook, piles and piles of them, and they eventually do turn into books, portion of books. This is kind of called the Polyphase pamphlet, but it really is kind of a brief excerpt of his presentation from this year. And Griffin was kind enough to kind of do a lot of the editing and transcription, putting the notes and the diagrams into book form. Simon Davies in the UK with TeslaScientific.com. He helps with a lot of the formatting and stuff. And then I try to put these into an ebook form. And this is on Amazon. So if you go to Amazon.com and if you just type in Dollard and Polyphase, you'll see this book here with this exact cover. This is just a proof copy with this little label across it, but it's basically about 90 pages or so. It's do you want to kind of just go into a synopsis on what this book is about? And this is also an ebook on emediapress.com. But if you want to just give kind of an overview on this, Eric, because hopefully
this is the first chapter of my presentation that I gave on four-phase. So right now, that would be volume 1. Presently, I'm writing volume 2, and I think there's 5 volumes altogether, and then I'll write up the whole presentation. And it's the same thing with the four-phase Bach presentation, working on that also, which is a lot more difficult because I have to transcribe the entire piece of music. So that's pretty much takes up about most of my time during the day. So those are the 2 main things right now. So the book that's out now is kind of gives you an idea of the kind of the theory of four-phase in very simple Pythagoras type terms, and then gets into a detailed presentation of what Tesla and Westinghouse did at the Chicago World's Fair. So I don't think anybody thus far has really presented how all that works and how the four-phase was arrived at. In fact, actually, there's people on YouTube that are confusing the issue, and that's one of the things that initiated me to make this presentation, because there's a lot of bogus information going on, particularly amongst the anti-Tesla crowd. So it's all basically pretty simple, geometric, mostly historical pictures and diagrams of things that were in operation at Chicago. And then there's an appendix that shows all the important diagrams and photographs of the next system that Westinghouse and Tesla built, which was Niagara Falls. But I didn't write that up because it kind of been more of just a repeat of the Chicago thing, and I wanted to keep this as brief as possible. So that's basically what this booklet is presenting.
Okay. And, hopefully over the weeks, people will be able to get their hands on a copy of the paperback as well as the ebook. Look through that. And if they have any questions, we'll be doing these calls on a regular basis. Just after the conference, I got so swamped with so many things, and everybody's been busy with the projects that we haven't done these for a little while. But we like to do these, I don't know, roughly about every 3 weeks or so. Would probably still work for everybody if
perhaps
We'll
once a
see
month,
how the
Aaron?
schedules work out.
Perhaps once per month.
about once a month or so. Yeah. Let's see. Okay, so Griffin, if you want to take over and start talking about some of the work down in Tonopah, I think you should have screen sharing enabled if you have a slideshow that you want to start going through. So it'll be talk about the Tonopah, then we can bring Justin on to go over the long line stuff. And then I guess then you and Jeremy can cover the coil stuff, then we can hit these other topics.
Okay, we'll start off with the coils. So let me begin sharing my screen. Can everyone see my screen?
Yeah.
Okay. Okay, and Haka says if you would like to chime in on this, go ahead, because you
Absolutely.
also worked along this. So over the past episode or work episode, which commenced in Tonopah during the early half of this October, we conducted multiple experiments involving a modified coil designated for the 160 meter band. Initially, with the help of Hakases, we were able to recreate this coil by adding winding forms along the side of the coil to lessen the number of turns and ultimately allow us to gain to broadcast in the desired or intended frequency range, which was the 160 meter band. In previous live calls, we displayed this coil before, in which it had a greater number of turns and ultimately did not have the desired operating frequency. So here we see the modified coil sitting atop the Telluric test platform in a testing configuration with a Navy-style signal oscillator for initial experiments and analysis. This is a larger depiction of the setup. And here is the initial analysis with a frequency generator and a signal strength meter. So we are essentially characterizing how the frequency has changed with regard to the type of wire gauge and as well as the number of turns, since it is
just to add, so the last trip was essentially to finish the ground project, to get the very low impedance ground in operation. And in that last trip, we didn't have a lot of time to do long range experiments. So this was the first sort of recreation of the past test that we were able to go down more methodically and better characterize and do a better performance test of the system that had just been finished in the previous.
Okay, we'll continue. So throughout the course of the experimentation, we found that by adjusting a variable condenser, which was situated atop the coil, that effectively allowed us to change the frequency. And here, as Hakases was setting up the test configuration for transmission through the Earth, the operating frequency in this circumstance was 2.3 megacycles. Hakases, if you would like to elaborate more on this.
Sure. So there's always some level of tuning. The coil that you get is never going to be exactly the way you want. In what was actually good for us is it was slightly above the frequency range that we were looking for. And with the help of Eric's guidance, using the overhead aerial and a variable condenser, we were able to essentially change the loading slightly on the upper half of the coil, which allowed us to tune all the way from about 2.3 megacycles to about 1.8 megacycles, which was perfect for the 160 meter band, which fit perfectly with the equipment that we had. So we could actually do tests that were more than just very simple, quarter watt frequency generators. We could actually start putting some power through and doing better long range characterization.
And here is a depiction of the signal strength meter responding to the natural period of oscillation on the coil at the given frequency of around 2.3 megacycles. But as Hakases said, this frequency range was quite variable given the adjustment of the variable air condenser. And this is the impedance matching transformer, which was employed.
I believe it was 6 turns. Was it 5 or 6 turns on the high side and then 2 or 3 turns on the low side?
Correct. So it was 2 turns. So okay. Ultimately, this type of ferrite that was used, it was a stack of 3 individual number 43 ferrite cores which was wound likewise with a specific number of turns to match the impedance to that of the coil and with respect to that of the tank ground. But as found in previous work episodes in Tonopah, the utilization of ferrite rings for this type of operation is not suitable whatsoever. Ferrite does not pose as a favorable means to match or to create a form of impedance matching between such a low impedance and that of the coil. So we had to find that out the hard way. And likewise, there will probably be steps to mitigate this problem in the future where we will not use ferrite. And this is showing the ground current that's being pumped into the massive water tanks below this deck. This is showing,
which was
Go ahead.
both a way. So the thermal amp meter gave us a direct reading of how much current was being pumped in and out of the ground. And when we're getting up to a certain amount of power, it gives us a dual purpose of not only determining the number of amps that's being transmitted through the ground, but it also gives us a way to characterize the entire system because you can reverse engineer based on the watts in what the standing voltage and thus the current and thus the system impedance in operation. So it gives us a very good idea to characterize this coil and help tune and match to it. So it fits the 50 ohms of the transmitter with the, X, which might be 5 to 20 ohms on the Tesla coil side.
and shown in this picture, this is basically our maximum current that we were able to achieve going into the earth, which was around 2.3 amperes, RF amperes. So with that, Aukasys was able to conduct a test, a long-range test, in which how much power
So our initial test, we began at about 80 watts or 80 to 100 watts. And these tests were performed over approximately 24 to 36 hour period. The initial test was performed with 80 to 100 watts, and we got a clear signal approximately 115 miles away with another site in the evening. And we gradually turned the power lower and lower and lower to find out what was the minimum amount of power that was required to transmit that distance and make a successful one-way contact. Eventually, we brought the power down to it was between 4 and 5 watts, and we were still able to get a clear signal over 100 miles. And what's interesting about it is because normally these systems, normally the 2 meters band requires a very large, very long antennas, often hundreds of feet long. The hams that actually work in this band tend to work on farms because they're the only people that can get enough land to get antennas 200-300 foot dipoles across to actually make viable contacts with this. What's novel about this system, even though it may not be ground operation or it may not be completely grounded or it might be something conventional about it, it's still novel in the fact that you can't really see it well in the picture, but our antenna is approximately 10 feet across, and it's not designed to transmit. So the end result of these experiments is we were able to make range tests that were significant beyond what is normally possible with a ham radio of this configuration. So it's essentially a new type of ham radio at the very least.
And this is a picture of the overall setup with the transceiver, the ICOM transceiver, and a respected antenna tuner that's connected to the coil assembly and that to the ground tanks.
And you can kind of see on the top above the coil, there's the approximately 10-foot aluminum aerial, which I guess you could say serves as the antenna in this case. And then comparing that to a normal.
Actually, it's a capacitor. It's not an antenna.
Right, but it may be a radiating surface. So we are just calling it an antenna for the conventional sake. It's not designed to transmit from that function, though, I believe, right?
No, it's a capacitor, loading capacitor. That's why it's in the form of a T to help cancel out the electromagnetic effect.
Right. So it's a different kind of radio than the hams would normally use.
It's electrostatic, it's not electromagnetic.
Right, exactly.
And in this configuration, we were able to achieve a long distance transmission, and we received from the person at the receiving end a decently clear signal at relatively low power levels.
So let me
Between
point
4 and
out at the receiving end, there was not another one of these transformers. We have not gotten to that point. All there was just a scrap of wire 40 feet stuck into the back of a receiver. So we're doing pretty good with a totally impaired receiving system at the other end, and it's still picking up with 5 watts.
And granted this mismatch, we were able to obtain a transmission distance of about 114, 115 miles on only a couple watts, which is rather significant. And this gives a overall depiction of just the line of sight perspective between the transmission and the receiving setup.
Mm-hmm. The only other thing I would point out is we did the tests over a significant period of time. And while there may be a telluric component or something going on, we were not able to get successful signal transmissions until the evening, which was when the 160 meter band conventionally opens up and allows that type of aerial propagation. So it's still worth a lot of study what's actually going on and what characteristics we're doing. But we do know with a completely unmatched system that we're still able to get pretty incredible results using this. So once we have a pair of matched coils at the same distance, who knows whether we'll be able to get more significant results or at least better characterize the results.
Right, and this covers the experiments done with that coil, the modified 160 meter coil. So now we will cover experiments that were conducted with a scale model Alexanderson coil. For those not familiar with what the Alexanderson coil is, we see here it is essentially a type of potential coil used in a generalized fashion in the Alexanderson method of transmission. We see this as an actual coil used at the SAQ station in Grimtown, Sweden. It roughly stands about 6 feet tall, just the coil portion itself, and is about 8 feet wide. It has 10 different layers, essentially a pancake wound type layer with 8 turns in each layer. It's a rather unconventional type of winding scheme, which is seldom seen in conventional or modern day practice, I should say. And for this purpose, it was we had the desire to investigate this design. But of course, this actual construction is monstrous in proportion. It was necessary to produce a scale model of the setup. So here we see an approximate 1/7 scale model of that very coil, having the same 10 layers, with each layer having about 8 turns. Now, this setup, it was used in a very similar setup and configuration as the 160 meter coil was, as it was series connected in some tests with that of the ground or the water tanks below the testing deck, as well as being connected to a ferrite core, as was seen in the previous pictures. So, of course, this is the initial test with the coil, as we could see. We have a signal strength meter connected to the coil in an indoor fashion with the tank setup on the outside. We are doing the initial characterization of the coil, finding out what its optimum frequency is and what kind of frequency decrement the tanks pose on the setup. This is the outdoor setup with the Navy-style signal oscillator, basically producing the same analysis as was done with the 160 meter coil. Here's a closer picture of the impedance matching toroid as used again. And we could also see that in this configuration that we are utilizing the suspended aerial capacity, which could be seen with the brown insulator within the center of the coil. And this is basically to optimize, but also just to see how the aerial capacity affects the characteristic of this Alexanderson coil. And what was interesting about this type of coil and the way that it's wound is that it does not behave as a typically wound, helically wound coil. That this is a vector network analyzer plot that we took of the coil situated against ground, and we find that the red graph, which indicates the phase along the coil, as well as the magnitude of the coil at specific frequencies, which is indicated by the blue graph, that the dual moding effect, which has been covered in previous live calls, in which there will exist a mode which likes to transmit through the air, so to speak, the Hertzian mode, and that of the telluric mode, which has a tendency to be directed towards Earth if done correctly, that those two modes in a usual coil will be separated by a decent frequency range. But unlike that, in this Alexanderson coil, we find that that separation is rather small. Instead of being separated typically by in excess of 100 kilocycles, we find that there's only a separation between these two modes of about 13 kilocycles, which is rather narrow. Now, unfortunately, we lacked any decent power supplies of radio frequency to drive this coil, as its frequency was essentially in the broadcast band. We could not drive it to its full potential, so we couldn't necessarily characterize what the full capability of this coil was, but offhand, it was rather interesting to see that these two modes were essentially converging, which has not necessarily been seen in any other coil analysis conducted by myself, Hawkes's, or possibly Adrian.
To see anomalies.
The whole idea is to eliminate the dual moding and get the modes to be on the same frequency, but that would require figuring out how to make the Heaviside equation apply to the engineering of the coil, which is difficult because there's not really any mathematical formulations for calculating the things that would be necessary to plug into the equation. But just as a one-shot deal modeling the Bolinas coil scale model, it's damn close. So it's close enough that some minor modifications may cause a frequency unison between the two modes, which then will cause kind of an ultra resonance, which no one as of yet has achieved other than maybe Tesla.
Just a question there, Eric. Do you feel that it's possible to get the series and parallel mode essentially the same frequency?
That's the objective. It always has been the objective, but it's not an easy, it's hard to engineer it because
Yeah, indeed.
you cannot determine the so-called circuit constants from the geometry of the coil. No such formulations exist, even though I have come up with some pretty close approximations, but they're more suited for multiple conductor open wire transmission lines than they are wound coils. But at any rate, it's conceivable that that can be done, but somebody with a little more skill at the mathematics might have to help me with it, but maybe that wouldn't help at all. So I've put many decades of my life into solving this problem and have come up with the basic equations, but to turn them into engineering formulations is still lacking, but I'm close. So more experimentation is required, and that's what you see happening here is the experimentation, which is not easy because these coils, you just don't throw them together in an afternoon.
Exactly. Just to wind and create the Alexanderson form by hand was a rather meticulous effort, which spanned over the course of a couple days. So, of course, to manufacture something of a larger scale, larger size, it would take quite some time, but nonetheless, it could conceivably unify these two modes. But of course, that's highly skeptical at this point, but it is conceivably possible.
And even if we don't, even if it doesn't perform optimally in those circumstances, the coil has the secondary effect of being in a lower frequency range, which gives us the capacity to delve deeper, closer to the floor, to see how low we can get the frequency and see how it affects the impedance and losses over great distance, because we know Tesla tended to operate at a much, much lower frequency than what we've been using so far in the 160 meter band.
Right.
If I could just ask a question, this is for both Eric and Griffin. What is the primary advantage in this scenario of the Alexanderson coil over, for example, conventional Tesla coil?
It's lower frequency for the same basic bulk, and it also operates at a higher impedance.
Mm-hmm.
Right. Because
But
of the
Yes.
because of its configuration that, like Eric said, that the lower operating frequency, which requires a greater length of wire, that the same could be accomplished or wound on the Alexanderson form without having something of a larger proportion. And also from what I've measured is that, say, a helically wound coil of relative frequency to that of the Alexanderson coil, the efficiency, the magnification factor, the bandwidth of the coil suffers greatly in a conventional way. But unlike the Alexanderson coil, because of its geometry, it actually has a greater magnification and overall efficiency.
Mhm.
So
So
it's
if you wound a conventional conical or a conventional spiral Tesla coil, the turns would tend to be very packed together, which would give the coil a much lower impedance, or higher impedance. I forget which, but different characteristics to say the least.
It would increase the capacitance of the coil, and then the losses associated with that would be higher.
Right.
And the nice thing about the stacked pancake coil is by adjusting the separation between the pancakes, you can modify the mutual inductance and mutual capacitance to alter the operation of the coil.
So eventually in time, I'll be creating an engineering report for the effort that was put into the Bolinas coil, the Alexanderson coil, but as well as the modified 160 meter band for those who are interested in duplicating this coil, so to speak, or possibly seeking further information on just how this type of coil behaves. I'll be producing an engineering report that'll be on my website as well as on Eric's website in due time.
Griffin, just a question.
Yes.
On that current graph that you have there of the vector network analysis, do you have an expanded scan of the fundamental?
I do. It's just that it could not fit on the screen. It's
okay, sure.
Rather,
it would be useful to see that at some stage.
Yes.
Okay, good. Thank you.
Okay, and then moving forward, aside from the radio frequency experiments conducted in Tonopah, there was also significant work on the seismic mine, which Eric has mentioned in the past. So the seismic mine possesses certain equipment that was left over by a university. And in this picture, we are essentially creating a type of amplifier system that connects to those seismometers, which are found within the mine, which could convert to audio levels and be heard on this analyzing unit, which Eric is listening to. Eric, if you would like to elaborate more on what this is.
Yeah, it's basically a super heterodyne receiver that goes down into the deep, extremely low frequency band, because the seismic signals are like one cycle per 10 minutes, which are completely inaudible. So there's a Tesla converter modulator that converts it to about 400 cycle per second wave, which is audible, and then that's amplified by the telephone test set that you see me looking at. We didn't really have enough gain to pick up the background noise of the Earth. The amount of gain required for that is insane. But we did have 100 decibels of gain, so that's 10 to the 10th power. It's pretty good. So the way we got the additional gain was because we were using a loudspeaker to listen to it, there was a certain amount of feedback to the seismic transducer. And we got the situation optimized to come up with a stable positive feedback. And we actually managed to get about 1 minute of what the musical seismograph tone would sound like. It's kind of a spooky sound. And then we kind of lost it at that point. So it looks like before the Tesla converter, there's going to have to be a DC preamp, which I wanted to avoid because they tend to drift. And the problem with the drift is you can't keep the pen on the center of the seismograph. When you're getting the signal levels this small, which is 1,000th of 1 millionth of 1 millionth of a watt, reception gets very problematic, but we do have the necessary materials here to get to that point. But it's going to take a considerable amount of work. Do we have the audio of when we got we started to get the wavering tone, or does Justin have that?
We have it recorded, but it's not online at the moment.
No, it's unfortunate. Okay.
Yeah.
So this is a picture of the panel mounted arrangement for that. We could see that one of the core components which we were experimenting with was a electromechanical device, a vibrator, which is located near the center of the panel. And in this picture, we are essentially performing an analysis on the entire setup as a whole. This is the unit that would be taken into the mine shaft and connected to the transducer, and essentially the audio could be heard at the other end. This is the transducer that was left. It is a massive...
It looks a lot smaller in the picture. That is a massive piece of equipment.
It stands about 2 feet high, give or take, and it's located within the very depths of the mine, which we were working in. These are the other pieces of equipment that was left over by the university, and not necessarily in a favorable condition. Everything was just scattered all over the place, but nonetheless, we were able to work with it. This is a picture showing just the entrance to the section where we were primarily working in. The transducer is on the other side of where the photo is taken, but we could see the equipment, the panel, and what have you located on the floor on the right side of the picture. And this is the entrance to that room where the main experiments were occurring. So this mine has been a long project going for at EPD Laboratories, and I'm sure Justin and Eric could expound upon this afterwards. But nonetheless, this main project covering the amplifier was decently successful, but it did pose limitations and it did have some problems, as Eric was mentioning just now.
And I guess one of the things is that this was a seismic monitoring station that was put up by a university that was essentially abandoned. And by picking it up and moving it forward, we're not only bringing it back online, but more than likely adding additional capabilities in a certain mode that people aren't usually used to for it. So that's sort of the main purpose of all this.
Well, the end result, it'll provide an audible presentation in stereo of all the seismic activity within the Earth down to very minuscule levels. This is kind of an extension of what I was doing at Landers. The big hang-up here is getting the necessary excavation at the portal of the mine, because it's partially caved in and there's no way that we can, put racks of equipment in or what have you. And that is a very expensive, difficult task. So that basically has snagged the project. But at any rate, inside we do have the necessary transducers, and that will allow for experiments like you're seeing to see if we can get the amplification up to the 130 decibel level.
This is the musical seismograph project is the end goal of this.
Yeah, so it's a 3-axis north, south, east, west, and up, down. So I've come up with an audio system using a Pythagorean frequency scale where the three tones will all be in phase coherence, which will enable it to be in stereo. So when you're sitting in between this geometric network of speakers that matches the seismic transducers, you in essence will be inside the earth and you will hear all these waves running around, and north-south would be one frequency, the east-west will be another, and up-down will be the third. I made a rather extensive video presentation of this called the Musical Seismograph that deals with every aspect of the project, the amplification, the special amplifiers, the way to generate the frequencies, why these particular frequencies, and numerous others. About 4 hours of material. It's basically a complete college course on the subject. I don't think there's anything like it's been presented up to that point.
Question for you guys. What's the frequency range that you're kind of seeing is the majority of the usable information that you're trying to extract? I mean, Eric, you mentioned one cycle for every 10 minutes, but is there a much broader range for that? And obviously,
it's much broader. Some of it is actually directly audible. The basic frequency band, the bandwidth of the input side, in other words, the seismograph side, is DC to 400 cycles per second.
And do you have any sense of exactly what the various bands, I mean, if you took kind of a log scale of all of that, what frequency band relates to particular geologic activities and what you're looking for?
Well, that we have to build it before we can do that.
Yeah, okay.
So
Right on.
basically anything like this, the frequency distribution is 1/f. So the lower in frequency, the stronger the signal. That's kind of a natural curvature. It's called 1/f. A lot of noise operates that way. The system at Landers was not connected to any audible devices directly other than an alarm system. So, but there was the oscilloscope, and you could actually see the sounds of rocks cracking and what have you. So that whole system was a 130 decibel gain. It was very difficult to keep stable. It was an absolute nightmare, and I had to resort to some undesirable techniques like series capacitors and what have you. But nevertheless, it probably was the most sensitive seismic system in existence. When you look at the oscilloscope, basically the ground is like the surface of the ocean.
Yeah.
There was never a straight line on the oscilloscope. And there were frequencies there that would be audible if it was put on an audible amplifier, the sounds of rocks making noises and what have you. So this is a much more advanced version of that. And but like I say, there's a lot of obstacles in finding a contractor to do all the excavation and getting the concrete in, and I don't know. That would take some serious donations, which don't seem to be forthcoming. So this is about the best we can do right now. Is periodically we'll go inside and hook things up, and we do have one audio, but unfortunately that's not available, and it looks like Justin didn't make it. So I guess we won't have any of that material presentable, which is unfortunate because there's a lot of man hours of work that went into all this, and we're not able to show it.
Well, hopefully we'll be able to get it up maybe next month when, said, don't sweat it now. I'm sure it'll be coming.
Okay, yeah, this is
I just wanted to jump in. Actually, Justin Miller is on this call.
Oh, hey.
Is Justin here?
Okay.
So here, Griffin, before we get too far, I was told that whoever's speaking, you can see them in a little thumbnail at the top right of the screen, correct? Like everybody's able to see that?
Correct.
Okay, somebody messaged me that might not show up on YouTube, so I want to make sure that whoever is speaking.
Were you thinking the vocal comments or chat?
Neither.
Okay. Well,
Let's see,
are we
standard.
able to proceed?
Yeah, hold on a second. So if you're talking, then your screen should come up. But if it's during a slideshow, so basically whenever anybody's talking, if you got a slideshow, I think the only thing that the Zoom recording is going to catch is what's on the slideshow,
Okay.
which is okay. So I mean, it'll at least get the audio, but it won't actually show who's talking. How many
Okay.
slides do you have left before we go into any other main topic with Justin's presentation or anything else?
This basically covers all that we did. I'm going to hand it over to Justin to speak on the Long Lines project.
Okay, let's see if there's any other. Does anybody else have any questions before we move on to Justin's slideshow?
Yeah. Hi, my name is Aiden Schaefer. I'm working or I'm involved with the Alt Propulsion Group, the Alternative Propulsion Engineering Conference, and the setup with the coils and you're getting over the horizon communication. That was pretty cool. What the question is like, have you guys played around with transmitting near or slightly below the von Neumann resonance and seen any strange feedback or anything? I mean, I'm talking like just right in front. Like if the von Neumann resonance that day is like 7.5 hertz, you'd be trying to transmit at like 7.3, 7.4 hertz. So, or have you
If it was a
danced around?
that would be
That
massive.
stuff is still under construction. The 4,800-foot long electrostatic ionospheric antenna will work in those modes, but that's a ways off. Anything to work at those frequencies is going to be enormous. Otherwise, you're going to be dealing with goofy coils and and things. And to actually make an antenna to work at those frequencies is quite a challenge. Or to make a Tesla transformer to work at those frequencies, you would have to have maybe a 700 kilovolt substation transformer. Primary coil would work good for that, but that's not something that you're going to fit in your backyard. And the interference levels can be quite extreme from all these LED lights, and the electronic digital silicon interference is basically going up exponentially with time. And before long, it might not be possible to receive anything.
Okay, so I'm hearing that you need a very large power source, and it's
Not a lot of
again,
power. Doesn't take a lot of power. It takes a lot of inductance.
inductance. Okay, and but
Big,
the
big
size.
antennas, lots of coil,
A
lots of power.
700,000 volt substation or generating station transformer probably has an inductance of several tens of thousands of henries, and maybe as many as 50 miles of wire wound on the coils. So that's difficult. But the original Long Lines project was before it got torn down. That I tried to intervene on here was a 70-mile long open wire carrier telephone line, and that would have worked quite well, but it got torn down. So the best we have now is 1 mile, and which is better than nothing. It's not something you're going to get in the backyard, and it's away from direct sources of interference. So we should be able to start to do analysis of those lower frequencies, and it would go into the super heterodyne converter to get the frequency translated to one that was audible, because we can't hear 7 cycles per second. So it would have to go through
Okay.
a
Yeah, this is
heterodyne converter.
so this is just from the group at Falcon Space and such. We're working on flying saucers and trying to demystify some of the field mechanics, and we've got some data that came out of White Sands, and it was showing that the saucer was generating an ultra low frequency that was just right in front of the von Neumann resonance. And I can see that would create, or these frequencies would be similar to in size to the Earth's field. So they're generating like a bubble or some exotic field topologies around the vehicles and interacting with the density of the local magnetic sphere at that at those frequencies. So it's just, if you guys are doing communication and you're able to like tune in down to that wavelength or that bandwidth, you might hear something. So that's just a friendly hello from from our side of the RF engineering aspect of this. So anyway, fascinating discussion. I'm going to drop back into the background and listen to you guys some more.
Thanks, Ed. Okay, so we move on to Justin's slideshow.
Just one other quick question, Aaron, is I was really intrigued by, you know, all the geometry and the work you're doing with the Anderson coils. And I was wondering, you know, if that series and parallel configuration ever really gets tuned up, does anybody have kind of a rough estimate of kind of gain you would be getting out of that configuration over a standard coil configuration of broadcast?
It would be greatly improved.
Somebody's got some noise going on there.
That was Justin. I can see your video in a little thumbnail, but you have a different connection on here without a video, and that had a lot of that background noise.
Interesting. So I have two different browsers open, or two different connections to the call. The silly phone is what's working in real time to hear you guys and keep up on this call, but the slideshow is on the laptop and it seems to be running slow, or maybe it's not going to allow me to share my screen. So I did send you those files, compressed zip in Signal. I don't know if you might be able to show that slideshow and I can just talk about it from the silly phone.
Okay. And Ken, did you get your question answered, or maybe somebody can answer that while I'm pulling up Justin's slideshow?
Yeah, it kind of got garbled, so I didn't really pick up any answer there.
Yeah, well, I would expect that when the thing's brought into consonant resonance, its performance would be greatly improved.
100 times, 1,000 times?
Well, it's, you know, it's speculative.
Yeah, okay.
But instead of the two modes fighting each other with the beat frequency, they'd be in coherence. And this is something that Tesla probably had learned how to achieve, and that's why his stuff performed way beyond what anybody's able to do today.
Yeah.
I would just add to that, but in principle, the series and the parallel mode, they are in coherence. They are joined together in the same coil. So in principle, they are in coherence.
Right.
No, I mean, they're the exact same frequency in the exact same phase.
They can be in the same phase, but they don't necessarily share the same frequency, but they can still be coherent.
Yeah, but if they're not sharing the same frequency, it's like if you got a 60-cycle generator and a 50-cycle generator, you can't parallel them without seeing the big blue flash.
Yes. No, indeed.
Good point on that. Thank you.
Okay, I'm just about ready with Justin's.
Actually, I got my screen sharing up on the laptop and it seems to be working pretty good. So I'll just do audio on the silly phone and screen share from the laptop.
Go for it.
Okay, so I started in with this slideshow. I'm going to try to move fast. I got a lot of slides. This episode was the third episode of the year. We had one in January into February and June into July. And then this final episode was October into November. And so I'm starting out. This photograph is kind of the beginning of the episode, or where I wanted to jump into it. You can see Eric, Hakases, and Griffin and the dog all here at the seismograph mine. So some of that material is already covered, and so we'll just move along into basically I was facilitating what the rest of the group was doing while those guys were there, and then once they left, then Eric and I went back out into the field and began on this long lines project. So here you have a section of the line that's closest to the shack, and this is what we focused on this particular episode. The entire right of way that we have is quite extensive, but we don't have the funds or the proper equipment at this point to tackle the whole thing. So we've just decided to tackle a portion of it, which would be this portion that I'm going to show in this slideshow. So we start off with a lot of the heavy lifting has been done at this point in time. We've got poles up and we've got cross arms on the poles. And in some cases, we even had to do some modification to what was there, but we'll get into that as we progress along. This is the section of line that's nearest to the shack that we began our work on this episode. So this pole is this is a terminal pole. This was intended to be a dead end pole where the transmission line meets the effectively reception antenna, we can call it that. And Eric, please feel free to jump in and correct any of my terminology as we go along. So this is kind of a historic rebuild of Bell System open wire telephone line, and being that it's a historic rebuild, we also have historic hardware that we're using. A lot of this is old hardware that we've salvaged from other lines that we have cleaned up along the way. And so quite a bit of work in the past has gone into just inventorying all of this hardware so that we could be successful and build this. This is a good representation of that same, what I'm calling a terminal pole or dead end pole with the shack in the background, and it kind of starts to give you a little bit of a sense of the scale of this thing. So this episode, we decided on some construction that we sort of were finding our way along the way. We can scale this up, and we were intended, as you can see on the cross arms here, that we were intending to have ultimately there'll be outside conductors all the way out of the extremity of the cross arm. But for right now, we're just focusing on what we call the pole pair, which is nearest to the pole central in the cross arm. So you can see me there beginning to make some modifications to this arrangement such that we can put up that pole pair. A lot of custom fabrication went into it. You can see some of the work laying out these shorter cross arms. And this is one pole in particular, because we're building with an old right-of-way that was what was the cable TV right-of-way in that town. This particular pole had some rot issues, and so we had to do a structural fix, kind of a patch at the base of this. And Eric moved a lot of rock to be able to accommodate that patch.
Let me point out that pole is 120 years old.
120 years old, yes. So this pole has, we can tell that by looking up at it. It's got 3 gains cut in it. And the gains is where the cross arm, horizontal cross arm would meet the vertical pole. They cut a notch into the pole, which is called a gain. And we can tell by that configuration kind of the vintage of this particular pole. So it was dug out of the ground after it was done with its service as a telephone pole, and the cable TV company glommed it and put it in. And now we've repurposed it and we've splinted it up so that it can continue its life as a utility pole here in the desert.
Justin, it also means that pole was essentially around doing its service 40 years before most of us were even born. It's something.
Right, yes.
Before our grandparents were born.
Indeed. It puts it all into perspective, I think.
So it started off as a Bell telephone pole, and then it was glommed onto by the local Tonopah telephone company, which would have been about 1905. And then the cable TV company got a hold of it in the early 60s, and then we got a hold of it, and the termites have pretty much finished off the bottom, and all the rest of the poles in this lineup fell down, rotted, but this one, we tried to pull it over with the truck and dig it out to put a new pole in, like we had to do with about 20 of them along this right of way. And it didn't pull over. So it's a scabby, ugly looking thing and what have you. But because it wouldn't pull over, then we did the splint job. So we put a braced cross arm at the bottom. What you normally do when you're mounting poles in swamps is you have a kind of an A-frame type thing on the bottom that prevents the pole from falling over. So the wind load, storm load is transverse to the line. So we reinforced it heavy that way. And then we took some barbed wire fence posts and pounded them around to splint it up, and then moved in about 800 pounds of rock and got all that down in there. So it'll last, it'll definitely last the rest of my life.
Right. So these are good points to Eric's bringing up, and I want to just sort of echo what he said, that there's been a lot of pole replacement, and this particular one, we made an attempt to knock it over. If you've got a pole that's got a rotten base, we found that this ground is very difficult to dig in, particularly to dig 5 foot deep pole hole. So if you've got an existing rotten pole and you're able to knock it over, you can usually clean out the old hole, clean the wood chunks and termite debris out. But in this case, this pole would not pull over. So we just decided to splint it where it was. We didn't really have any other choice given the equipment that we had. But we have done quite a bit of replacement of poles, which also means on the other end of that there has to be procurement of poles so that we have the raw materials to stick in the ground. But moving on in the kind of historical nature of things, of this project, doing things in particular in this terrain, there's been some discussion in previous calls about having some more elaborate apparatus like a bucket truck or a line truck, which we can talk about for future episodes, but really it wouldn't even be appropriate for this particular terrain. We found it's too steep back there in the draw moving up to the shack. So really this is the only way to do this kind of work, is it has to be done from the ladder. And then there's also a point at which the ladder, it just makes more sense to put the climbing spikes on and spike around the pole to do some of this work. So this is, these photographs are in time sequence, just moving through this last episode. So what we're doing is we're finishing outfitting these poles nearest to the shack such that they can carry the transmission line section of this facility. And you can see that moving on up the hill towards the shack. That's in the near ground is the pole that we had braced. You can see the crossarm arrangement in the dirt. And then we're just making our way on up, putting up those small crossarms for our transmission line up to the shack. We had an interesting occurrence. It was a kind of a daily occurrence where we just worked until the sun went down, basically. The weather was perfect. We really lucked out as far as the weather went. So we were just able to work until we ran out of daylight on a daily basis. And as we're marching up the hill, the sun is setting down behind us. And I included this photograph just to show Eric knows what this is. So this is what we used as our neutral wire. And this particular clump of wire was something that I had glommed from Sacramento several years ago. And it was on a wooden spool. And I thought, oh, great, this will be really valuable for the project. And I brought it back to Tonopah, and it sat in the backyard, and almost immediately the spool disintegrated. So this just illustrates, there's not any documentation that I have of the process of uncoiling this. But this is thousands of feet of wire, and it took me a day and a half, and I uncoiled this. We ended up actually using this as our neutral wire. So I just included that to show kind of the level of background work that goes into our projects because we're working with old material or salvaged material. So here we are at the shack, actually ready to get started pulling wire down the hill. And you can see I brought all of our ladders up there to try to make this an easier process, because we'll need to be on multiple poles, on the shack, on the main terminal dead end pole. And so we're just there's a lot of tools and hardware that go into all this. I'm just trying to kind of illustrate that. And this is now the terminal dead end pole at the shack, where the lines will all effectively dead end. And then you can see our transmission line across to the shack. And we chose to use those wooden side bracket insulators. Go ahead. I just heard a sound on the audio. I thought somebody had a question, but I just keep moving along.
Justin, I do have a question. I mean,
Go ahead.
how many wires have you got terminating there? What is the wire arrangement across the poles?
What we have there is we have on this wooden side bracket insulators, which some people may recognize from their youth or such. There are some places in the United States where this is still being used. But right there, that will be our transmission line. There's a pair of them on the blue insulators that's coming across. That's our transmission line that connects the antenna structure to the shack, which will ultimately terminate in the shack. And then there's a set of cables above, which mainly that carries our coaxial cable for the antenna above me on the cross arm there. And that's our voice repeater, or our radio link at the hilltop. 2-meter radio.
And how far do those wires extend, Justin?
Let's see if there's another picture that shows. I'm sort of skipping here. They're not very far. I'm trying to get perspective.
About 40 feet. About 40 feet.
Mm-hmm.
Yeah, not very far between the terminal pole. There'll be a picture here upcoming that I think will give perspective as far as to how far this terminal pole is away from the shack. But like Eric says, 30, 40 feet. It's not very far away. Mm-hmm. So then we have here is again a relic. This is a wire reeling machine that we got from Steve Hills procured this for us. And this is not actually meant for this purpose, but it's what we have. We actually have 2 of them, but I discovered that one of them is not functioning, and I don't know that I can make it function. So we just ended up using just this one machine. So there's that same cluster of wire that I showed in the previous frame. I said we were going to use it as our neutral wire. It's all salvaged, rolled neatly on this reel machine, and we're going to pay it out. So here is now the first wire going up. This is a big day for Eric and myself. This is a real moment of success. To anybody else, I mean, yeah, it's a wire up on the cross arm, but this is big. So the tensioning process, I wanted to kind of show there's a lot of up and down, a lot of rigging, a lot of pulling up this way and then going down and looking at things to back and forth determine exactly what the wire tension should be. So in this frame, we've got the neutral wire up, and I'm actually pulling up the first conductor. This is number 10 copper weld. That same wire reeling machine that you saw in a previous frame with the neutral wire on it, we used that wire extensively to salvage a lot of this, what was open wire telephone communication wire that we went out there and harvested, cleaned up mess of the old telephone system that had basically been abandoned because there is no Bell system anymore, and none of the current iterations of phone company want to take that liability on, or that responsibility. So at any rate, this is actually the other end. I was showing the terminal pole at the hilltop shack. So this is the other terminal pole down in the draw. We've got 3 wires up now, and we're making steady progress. At this point in the episode, our friend Connor came out, who was somebody that we had met at the ESTC conference this year, and he approached us about wanting to come out and work with us. So we made arrangements.
Can I interrupt for just a second?
Go ahead.
That's your transformer in the background, Adrian.
I have to say that's good. That's good to see. It's just,
How do we make it appear in your shop?
he's just right now in the wrong country. We'll work on that. We'll work on that. But it's good to see it.
Wrong continent, but we'll have to figure out how the trucking goes for that. Probably
the intent is in the right place. We just have to find our way.
That's right. So Connor came out. We met Connor at the ESTC conference this year, up there at Aaron's shop, and he wanted to come work with us. So we made the arrangements, and he came out. He was awesome. Connor jumped right in, salvaging or helping to repair this salvaged repeater cabinet, something that Eric and I salvaged. To give everyone an idea of the extent of the long collaboration between Eric and myself and the scope of the project, before there was an EPD Laboratories Incorporated, before there was the building in Tonopah or the right of way or any of this, Eric and I were gathering pieces with this, some general concept of this in mind. So about 15 years ago, Eric and I salvaged this cabinet, and we were finally at last in this episode able to put it back into service. But it needed cleaned up and it needed some repairs. So Connor got into that and immediately fixed that up. And then back out on the line, it was massively helpful to have an extra man out there and be able to run back and forth and be able to be at a distance on the radio link, talking to us at the hilltop over our radio link to say, how high a conductor was in relation to the cross arm, or that they were of equal tension. And then I was able to make adjustments back at the terminal pole. So really pleased that we had some help out there. We keep saying, that we're done with any kind of earthwork, but then lo and behold, we find another reason to dig. So there was a previous episode, there was a guy anchor that Eric and I installed, which became damaged.
But Justin, you love digging. You love digging.
Love it. Absolutely. Give me an excavator. I would love to dig with an excavator or a line truck with a big hydraulic auger or something like that. But we don't have any of that, so we do it this way.
And it's so much satisfying with a spade and shovel, huh?
That's right. Yes. We have quite a relationship with this digging bar. So just wanted to show again, the team effort here or the collaborative effort of having multiple guys on the project at once. It was, things started to actually really move quite quickly, having the extra support. And our volunteer, Connor, he was really into it. He was gung-ho and wanted to get up there and climb poles. So I said, go for it, man. Just set him up. And I actually got to stand back and take the picture of somebody else working. So it was huge. Just kind of wanted to illustrate the collaborative effort that went into this. And also the complexity of, you can see there's a lot of tools, couple trucks, and quite a bit of equipment that we had to haul out there to do this. So what Connor's doing right here on this double cross arm arrangement, this pole actually could use to be upgraded. This is one of the original cable TV company poles that they put in, and it's too short and it's too skinny, and it's kind of a critical location. As you can see, it's not only a double arm arrangement, but there's two sets of double arms because the line changes direction. This is a corner pole in our antenna, and we have the pole, but again, the complexities and the tools and equipment that we would need to replace this pole. So because the anchor had become damaged and this pole is really not suited for all of that cross arm up there, we decided to actually take down what I had installed previously and just slim it down. We didn't need that much weight. In the future, if we're able to continue to build this line and we end up with more conductors on the cross arms, then we'll need to have the 10-foot cross arms. But just for our purposes, their immediate purpose, we were able to get away with skinnier cross arms. So we were able to eliminate a lot of weight up there on the pole, which also has sail effect. The wind was racking that around. So that's what Connor's doing, is getting rid of that.
Justin, just a question.
Go ahead.
How do you get to do all of this on these poles? I mean, presumably these poles belong, to example, to the telecommunications companies. How do you make all that happen so they don't come along and take down your wire, for example?
We are the telecommunications company.
Excellent. Good answer.
We have a public utilities right away, all the way to the building in town.
Good. So basically, you can do exactly what you choose with those poles.
Exactly. We're the phone company, so to speak.
Good.
Our poles.
Good.
Yep, these are our poles. This is our right of way with the various agencies that are involved. And we've just recently gone through a renewal process. So yeah, this is all, very official in terms of what it is that we're building. This is our right of way, our facility.
I just bring that up, Justin, because it's not a small thing. I mean, it just shows the significance and the depth in which the project is planned and put together and everything like that. That actually, in fact, you have your own poles, and you've
well,
made
that's
that
right,
happen.
and I appreciate that. Absolutely, that's something that I appreciate you pointing out, and I'll take that a step further, which is that this is something very unusual. I mean, where else would you be able to have this kind of facility? Where else would you be able to get a grant to have this kind of right of way? So yeah, Thank you, Adrian. Appreciate you bringing
for example, in the country that I'm in, you just wouldn't be able to do this. So
that's why we're here.
It's a big deal. Yeah.
Why we're here in the wild, wild west.
Indeed.
Hawkins has actually mentioned something earlier in this same call about researchers, or I can't quote exactly what he said, but he made reference to people using farm and ranch land to be able to have access to large enough tracts of land to be able to put up facilities. So
it's for the ham radio geeks, the frequencies we're working at usually need, hundreds of feet of wire. So it limits the number of people that can work in that field and experiment.
Exactly. Limits the number of people who can work in that and experiment, and makes you have to get creative about obtaining some kind of facility or easement or right of way, so to speak. So appreciate you bringing that to everybody's attention, Adrian.
Cool.
And I'm just moving through. This is another perspective of, I just kind of like some of these photographs because they show a bit of perspective. This isn't even, all the way back to town. This is just up to that one corner pole. So you start to get a perspective of exactly how big this facility is. And I put this pic in our slideshow to show every morning it's, got to make sure that all the right equipment is on the truck, because once you go out to the field, you really hate to have to come back. It's not that far between the building and the line, but a lot of time is wasted if you forgot a tool, a piece of hardware. The level of complexity, you can see there's digging tools, there's rigging, there's pole climbing equipment, there's pole hardware, there's all manner of carpentry tools. There's actually 2 trucks in this particular frame. Connor brought his own ladder, so he was able to work with all of his tools. Just wanted to kind of illustrate the complexity of what it is, and then you can see a little bit deeper into the truck bed. And as you can imagine, this gets really unorganized really fast. So you have to constantly keep up on it. Connor was gung-ho. It was awesome to have a second pair of hands out there. And he was really like a sponge. He was just so happy to learn any of this stuff. So this is a unusual picture where he was actually on the same pole as me, and I was giving him a demonstration on how to tie wire onto the insulator. So we're using, and you can see the kind of curly Q wire that's coming out of my left hand. That is actually Bell System salvage. That's one of their preform grips that's meant for this purpose. And then we used our own tie wire because it really doesn't make sense to try to straighten out the tie wire once it's bent. But Connor took some demonstration from me on how to do this, and then he went ahead and just was able to tie on the rest of the insulators while I went on to other tasks. So again, just really appreciate having the additional assistance this episode, and it made it happen. I don't know exactly where Eric and I would have taken the project to this session, but we certainly would not have gotten to the same level of completion, which means we would have just had to work at it, next episode or so. But it was great to actually reach this level of conclusion.
It shows the importance of the teamwork, huh? It shows the importance of EPD Labs work together.
Absolutely. This year for me, I've been involved with Eric Eric and I have been friends and collaborated on various projects and lived in the bushes together out in the coastal redwoods, since I think about 15 years now. We've known each other. And then EPD Laboratories Incorporated was started in 2013 for the purpose of a lot of this research. But it's only been recently that there have been these other collaborators that have all come together. And in fact, I was away from the project for a few years myself and have just really re-engaged the project. So now seeing this level of collaboration with all of these, all these really capable people, we're starting to see some things actually happen. It's very encouraging.
We just need some good donations in order to make all these things continue.
We do, and people have contributed along the way, and people are beginning to see our forward progress, and they're throwing in, again as well. We did have a private donor this episode who was able to facilitate some of my wages getting paid for this episode. So that's huge, and we're really hoping that that people continue to see the value in what we're doing, want to participate, want to contribute, want to be part of what's going on with EPD Laboratories and help further our research. So, that's a big part to me why I like to put together these slideshows and do these presentations. In the past, I haven't really wanted to do that. I've wanted to sort of sit back and I'll do the work, but I don't really want to talk about it or be in the foreground. But I'm much more excited now to show the progress and try to get people excited about the work that we're doing.
Well, in the UK, we have an expression: in for a penny, in for a pound. I guess in the US, it's in for a pen, it's in for a cent, in for a dollar, I suppose.
There you go. Well, that's it all takes, it's amazing what we've been able to do with very small amounts of dollars, but yes. It would be even more astonishing what we would be able to do with larger amounts of dollars. And as a sidebar, I think that's for the upcoming episode that we're planning right now. One of the things Eric's expressed that he really wants to do with this upcoming episode is start to put some price tags to some of these larger aspects of the project. Now what I'm showing in this slideshow right now is a, proof of performance that we've been able to demonstrate. We've actually done some of this in the past, and had various facilities. Well, Eric's done this at Landers, as many people will know. And that facility is no longer in our control, or possibly no longer in existence. We believe it's been bulldozed, but I don't myself really know. But at any rate, we're back at a point where we can show this level of demonstration, and we want to carry it forward. So based on having this,
how much investment, Justin, do you think is needed, or Eric, needed in order to bring this project to where it should be?
Well, it's scalable, really. I mean, that's why we want to sit down this next episode and really start to sort of hash these things out, because we could implement any number of, states of completion. And does completion look like a pole pair end to end from the hilltop shack to town? Does it look like a wireline telephone lease from the phone company that terminates at the mine? How do we network the facilities? So, we could end up with 6 or 8 pairs of conductors on this crossarm, which Eric's pointed out that the outside conductors could be used for noise cancellation. They could be used out of phase, pick up the power line interference, and then noise cancel that power line interference so that we have a more isolated signal, isolated ability to receive the signals that we're after. For right now, we just have a pole pair. So it's difficult for us to answer to exactly, well, how much money do you want? What's the scope of the project? What do you need to complete this? I think that's what we're intending to do, is to really hash through and have price tags for various states of implementation along the way, and
I
say,
think what would give an order of magnitude is approximately $250,000 has been spent thus far.
And how much, Eric, do you think still needs to be spent to bring it to a proper research completion?
Same again.
I would say, yeah, I agree.
I mean, basically, nothing's really been done with the building. I still don't have a real laboratory. There's no, the power's not installed. There's no heat. There's, the seismograph mine. That's another big expense. We have to consider, each time, like in this case, to get this, the next step now is to get this on the internet so people can listen to it. But then, that's going to be another communications bill every month. And like Justin says, there's orders of magnitude. $500 is a significant, things can be done. $5,000, $50,000, what have you, where we just adapt to the situation.
Absolutely.
And pretty much, other than what I need to put in my belly or the gas tank, I've been supporting this out of my Social Security.
Yeah, as we all are with all our research. Basically, we are personally and self-investing in our own research.
Right. Yeah, we
want to see it done.
Exactly.
Yeah.
Well, we do it because there's no other reason to do it other than just do it.
Yeah. It just takes a lot longer when you're using, table scraps to get there. So, we'll get there, but the funding goes a long way.
The way I'm looking, I'm 71 years old, and what Walt used to say, that the guy that I inherited the Landers facility from, which originally was built for him, he was my age, back then. He goes, it all sounds great, but will I live to see it? And at my age, that's what I have to start, I have to start looking at it like that. And also, I have to make sure that that there's people to pick up after I end up in a hole somewhere, so this stuff all doesn't get torn down and thrown away, particularly if it's offering some kind of public utility type service like seismograph to the town or to the university. These are all things I have to start thinking about this stuff now. So time runs out.
For sure.
That's the problem. Time runs out.
What we need more than anything else is a benefactor. So if anyone knows of a benefactor out there that may actually be interested in supporting this kind of groundbreaking research, then we want to hear from those people. Needs a benefactor.
And also, one thing that Aaron pointed out was to start making, amplifiers for sale, and Griffin's already got the prototypes underway. And I have amplifier designs. There's nothing like it in the world. So, but the problem is, again, it takes an initial investment to buy the materials to make the first batch of amplifiers. So it's the whole thing always revolves back, around to the dead end loop. Well, you can make money, but you got to have money to make money.
To start, yes.
But what's encouraging at this point, and I think Justin has the material, I don't know if we have any of the audio, like the one out of the seismograph with the reverberating, seismic signal. But this thing now, this antenna section, this first section receives, it's ready to put on the internet. That's the next step. I expect by the end of the year that their signals received by this antenna will be available to the public. There'll have to be some kind of minimal fee to cover, the communications connection costs, but we're really focusing on, finished, availability to the public services out of this. To get something out there, get something that works as the shortest path possible, but still, not, half-assing and forgetting about safety, and it's not like that here. This is all professional, and it's all up to National Electrical Code, and the government agencies involved are just delighted with how we're doing all this and how we clean the whole place up and how we're cleaning up the desert, of all these miles of abandoned wires that animals are getting their feet caught in. And so we're in a good position there.
So I want to clarify, Eric just said by the end of the year, and that it does not mean this calendar year of 2023. Next year. So, and
otherwise you best get busy, Justin. It is
right.
This year.
Well,
But
just
it is such that all circumstances optimized. If everybody was here, and it wasn't the ice age, we could actually, the hours involved and what have you, what's left in the year, we could have this on the air by the end of the year.
That's right. So to speak to that is that we have now the signals are terminated, these wires, and this photo that we're looking at, this is Connor on the pole at what is our temporary loop dead end. It's this reception antenna is intended to extend beyond this cross arm, and actually if you look really close, this picture doesn't show it too well, but there's insulators that continue on the other side of this. This will be a loading section where the conductors will be dead-ended electrically, but mechanically the line will continue from this point on. So we're just using this as our temporary dead end so that we've got our pole pair, and this is terminated all the way up to the shack. And so with a little bit more effort, there'd be some amplification at the midpoint where the reception antenna turns into a transmission structure, and the signals are then transmitted up to the shack. And then how exactly we get the signals out of the shack is still we're working on that process. And we have a number of different ways in which we might be able to get the signals out of the shack and beam them to town. Eric mentioned that there might be an additional communications bill. We know that we can use a wireless internet provider that's there in town, and they'll just come and hook up a dish. We may need to upgrade the power system at the shack. Well, we know at some point we will need to upgrade the power system at the shack. So there's a little bit more expense that needs to go into getting these signals actually beamed to town. And then we can figure out exactly how we make them available for what sort of public use or what sort of subscription base. But what Eric said is absolutely accurate. I just want to say it again, that if it wasn't winter time and we had the funds and everybody's schedules worked out, we really could in a very short order be able to make publicly available the reception of what's on these wires over Connor's head in this picture. We've reached that point. It's very exciting.
Hey, Justin, how many more slides do you have?
We're getting right to the end. I'll try and speed it up a little bit. So, here's just a bunch of really cool sunset pictures of Connor, and just again, wanted to sort of showcase the help of having him on site, on hand, me working on one pole, him on another pole. This just sped things up so much, unbelievably so. Now, here's that cabinet installed on the pole. And this is where Eric and I were able to actually connect equipment and do this, this demonstration, do this experimentation for this this
That's-
episode.
Hey, that's a nice sunset picture. That needs to go on a postcard.
Isn't that beautiful? Yeah.
Lovely.
So we just kept doing this. There's long days, working
Wow.
7 days a week for
Very
a
good.
month. I also use that opportunity to just point out that this is 90 days I was able to put into this project this year. 30 days back in January into February, 30 days June into July, and then this was another 30-day episode. So we're really starting to make some great progress.
But the important thing also, Justin, if I could just add there, the important thing is it shows the commitment of the people that are working with EPD Labs. Just how much we are putting into this.
Absolutely.
And what we would like is the reciprocation of those people that actually find this inspiring, they find it interesting, and they want to be a part of something which is pioneering.
That's right. I mean, donating to this project means that you get to be a part of it. You help to fund this research forward and see it to a state of completion that we wouldn't otherwise be able to do. We've been able to chip away at this nice and steady for a long period of time on very minimal funds. And we are excited about trying to kick this into high gear and move it forward at a quicker pace. So we're getting near to the end of the slideshow. This is just now this whole cabinet thing. I keep talking about this terminal pole with the cabinet is where the transmission line to the shack meets the antenna reception line. And that is why this is of such significance. It's also where the ground electrode network is. You've seen in those slides, I haven't really talked about, I've just been cycling through them, but there's a ground electrode. Obviously there's the overhead component needs to be tied to the earth ground. And this is where that happens currently. So what I'm showing is all the connections that come off of the line down into pipe, run down into the cabinet. This is a good one of that terminal pole with the shack in the background.
Justin, that previous poll was an important one. Can you talk us through the wiring? Go back again. And back one more. And one more. Go back another one. Yeah, this one. There's a lot of wiring there. Can you talk us through what's really happening there? Because it's key to understanding what's happening.
Absolutely. So what we're looking at in what I would call the foreground or at the top of the screen is where the transmission line comes from the shack to this terminal pole. And the cabinet's mounted below the frame on this same pole. So you have the neutral wire, which provides a metallic ground connection from the hilltop shack.
Which one is the neutral? Which one is the neutral wire?
That would be the central wire on the dark colored spool insulator in the foreground. And so that's the metallic connection that allows for conductive ground between the hilltop shack and this ground network that's below this pole, below this arrangement. The other two wires are at pole pair spacing on this crossarm, and they are the transmission line that would take any signals that are coming off of the reception antenna and transmit them to the shack. Eric has also expressed that with the 3 wires, we can also get another phantom pair. So we could actually put power on this same set of wires, which would allow us to use the hilltop shack's solar power system to power equipment at this cabinet without an additional power system. So that's what's going on that side of the crossarm. On the other side of the crossarm is where the field telephone wire that we're using for experimental purposes, ultimately we would like to use, we have actually, it's already been purchased, and we have hard drawn number 10 copper wire, about 5 miles of it that's sitting on the floor of the shop at the lab. And when we're ready to actually build this line for real, and we know that it's not going to get vandalized, or we're not going to be sorry, I just got a message on the side and I acknowledge that message. So the significance of this pole is basically, this is where the reception antenna meets the transmission structure, and it's wired through these lightning arresters. There's quite a bit of complexity. You could use conduit to route all of this, or in this case, we chose to use what are called bridle rings, which are these porcelain donut-looking insulators. I like the bridle rings. I think it gives a little bit more flexibility. And so all of that, the two halves of this current structure meet at this point and come down into the cabinet, where they also interface the ground electrode network.
Great. Thank you, Justin. That's good.
You bet. So I know that we're kind of running out of time in this call, and we should probably move on. I'll just real quick speed through the rest.
Look, I would just say, just so this is also to Aaron, that the Colorado Springs presentation is more than 45 minutes long. I mean, we can't just rush through it. There's a lot to show. So maybe it's not for this call. Maybe it's for the next one. Aaron, that's for you to talk to.
Sure. Yeah, that's no problem. But I'll at least point out the golden ratio and the Colorado Springs YouTube videos. So in the meantime, anybody who hasn't seen them can at least go watch it, and then we can go in depth on it.
What time are we at now?
Well, it's 2:41 right now, so we're an hour 40 minutes into the call. We could go to 2 hours, maybe 2 hours 15 minutes. There is a limit on how long Zoom lets me record the call, even with this paid.
Okay.
I mean, we need a good 45 minutes to do the Colorado Springs presentation.
Well, you can just do like an overview, and then for the next one,
I would prefer to do it justice and do it properly. If we're going to do it, I would prefer to do it in the next call, if that's okay with you, Eric.
Okay, well then we can concentrate a little more on this then.
Yes, indeed.
Too much to catch up on.
Do you have any of the audio, Justin, of the seismograph mine or the signals here?
So I have the only audio that I have with me is the open wire line demo that we did at the distant line several years ago.
That would be a good example of the same.
Yeah.
That's to give an idea of what we're listening to and what the type of signals we're looking to receive. So that might be prudent, I guess. Even just the links might even be good.
Sure. Well, the links, I'm sure that I don't have those links in front of me, but I bet that they could easily be put up by somebody on the group. How does video sharing work? If I'm right now, I'm doing a screen share. Can I just go to that file and open it?
It doesn't work, Justin. Trying to do streaming through the screen share doesn't work.
Okay. So I couldn't really share any of that.
You can do audio. You could do audio, but not video.
If I have just a video file, is there a way to play only the audio from that file?
If you try playing it on your desktop, then provided it's coming through your computer audio, then it's possible.
Okay, well, so this is basically the end of my slideshow here, and this shows Eric with the equipment that we use. There's the Bell System noise measuring set, which was previously talked about in relation to the seismograph mine. Next to it on the top shelf is the Steve McGreevy electrostatic receiving device. Below that is the good old-fashioned Simpson meter, and then right in front of Eric is the Sierra selective voltmeter. And those are the pieces of equipment that are critical. Those are the kind of tactical pieces of equipment that we're able to bring out into the field and do these demonstrations with. Ultimately, once we have the signals terminated in the shack, there'll be some more elaborate, more permanent rack equipment that'll go in there. And Eric would have to talk about exactly what that is. But this is what we used for the demonstration purposes thus far. And also, this is what we have used historically for various purposes. So I'll bounce out of this slideshow and let's see if I can open that that line demo file. So what happens if I start playing this? Is it going to choke the video, or do I just
I
close
think
it
it'll
again?
just look, it might look jittery, but I think we'll be able to hear it okay. We'll find out in a minute.
That's with so now there's a filter in this. This thing being that it's designed to measure noise.
Oh, that's weird. Hang on a second.
Take the slope.
You've cut the sound now, Justin.
Doesn't look like it's going to do the audio. It's got a reverberation.
When you start the screen share, there's two little check boxes in the bottom left where it says that, I forget exactly what they are, but they're basically saying to transmit the audio from your computer into the screen share. And if those are not checked, then what you need to go do is stop the screen share, restart it, and then recheck those buttons.
Okay.
They're all checked.
We got two.
They're checked. Justin started the audio. So Justin, if that sound was coming off your desktop, leave the audio on your desktop playing, but mute your phone, because the audio coming out of the speakers on your desktop is going into the microphone on your phone. I think that's what's happening.
It means we get you in stereo, Justin.
Okay.
Oh, mute the microphone on your desktop.
You need to unmute your desktop, Justin.
Basically all the players parallel. Against the ground, then we have our ground rod over there, which we use the bushes roots, greasewood bush as.
Not going to work.
It was worth a shot.
Well, one thing, the presentation called Electrodynamic Seismic Forecasting covers all it's got the audio, and it shows another system that we have that's already together. And so probably anyone that's really interested, just get a copy of that presentation for now until next time around. Maybe we can get the earthquake noises that we got out of the mine and the signals that we received off of this. But we're kind of just flailing right now with limited time we have.
Yep, I wasn't able to unmute my desktop without unmuting my microphone, and that was causing all kinds of havoc. So
we'll have to experiment with that.
that about concludes really what I wanted to demonstrate with this slideshow. I guess I will, if my computer will cooperate. It's thinking about it right now. Now it's decided to jump back up to the beginning. One more photograph I would share. I don't know if I'm still screen sharing.
Go ahead, Justin. You can bring it back up. I was trying to show the covers of Eric's videos.
Let's see. Entire screen. Share. Oh, this computer is moving really slow. There we go. Okay, so this last photograph here is from the other end, and it'd probably be difficult for everybody to see in this photograph, but the shack is actually in this photograph. It's about halfway between the pole in the foreground and the next pole over. It'd be very difficult to see that shack, but this gives a perspective of the entirety of the length of our right-of-way. This is not quite pole 0. Eric may know what pole this is, or approximately, but this is only 3 or so poles into the right-of-way. So I just wanted to use this as a kind of a conclusion point, just to illustrate that this whole project is scalable, and we have large ambitions. We're right now focusing on the realizable goals of what's in front of us, what we've been able to do with the small amount of finances and small amount of time that we've been able to commit to this thus far. And we have an absolutely unbelievable priceless facility between this right of way, what we have with the building in town, and the seismograph mine. We could never hope to duplicate this. So I just want to express to everyone the value and how unique this facility is. And with that, I'll turn it back over to the group.
So I'll point out that if these things could be finished, particularly the musical seismograph, the end result would be absolutely stunning. It'd be a number of these projects that Griffin and Simon Davies and I are working on and what have you would make sounds that nobody has ever heard before, ever. Both, in the music and in the scientific world, and that's what kind of gives me the inspiration to keep going, because I know what the end result's going to be, and it'd be phenomenal. So, is Griffin still with us?
I'm right here. I was going to say, should we dive into the amplifier or have that?
Yeah, that's important, because this is something that we're getting ready to turn into a saleable product.
Okay. So I'll start with that. Granted, we do have limited time. I'll go over this amplifier project briefly. So the amplifier that has been discussed in previous live calls, as well as by Eric, is utilizing a rather unique form of amplification circuit. In this case, in the realm of seismic forecasting, it has the goal of converting an electrostatic input to that of an electromagnetic output, but it is a rather unique amplifier where it is also intended for audio applications. So it is an instrumentation amplifier, but may also be used for high fidelity dynamic headphone use. So this amplifier is very experimental. Here we see the front plate of the amplifier unit that I have constructed. It's utilizing panels made out of other pieces of previous equipment acquired from different electronic surplus places within the Los Angeles area. But nonetheless, this amplifier, which has been designed by Eric, has proven to be rather interesting. This is the back panel of the amplifier. It utilizes a pair of double triode vacuum tubes. I want to note that this back of the panel was taken out of a different piece of equipment in which it was already fabricated with such fittings. So it was essentially required to place the necessary vacuum tube sockets in and other connecting terminals. And because this amplifier is interesting in the fact that it utilizes transformers within the circuitry of a specific value. In the meantime, we are using what are called telephone repeating coils to achieve the actual operation of the amplifier. This is the second panel, which has these two repeating coils mounted on. And of course, this entire amplifier produces a very interesting frequency response with a given input signal. So based off of my initial experiments, this amplifier has a range, a frequency range between 20 cycles and that of roughly 500 kilocycles, which is rather unheard of. And this is given with a variable oscillator input, and of course measuring the output of that amplifier with respect to the frequency. So this is basically a frequency response chart that shows the function of the amplifier. And because this amplifier has many uses, in this case it is being utilized within the realm of seismic forecasting. So we could see that the repeating coil unit and that of the actual amplifier unit is mounted in the configuration of the seismic forecasting rack, which has been developed over the last 2 years. And it is intended to serve as a much smaller version of the Landers facility, which Eric had constructed way back when. So we could see the various pieces of equipment which are working in conjunction with the amplifier. So taking a look at these two relay racks, we see that the right rack has the two amplifier units at the top of the rack. Underneath are the allocated chart recorders and other receiving equipment, which is allocated below. The battery and the power supply bays, which are located on the bottom of the right rack, can be seen, and on the left rack, those are other auxiliary pieces of equipment used for instrumentation and the analysis of the incoming seismic signals. Mind you, the seismic signals in this case are being received via a specialized Marconi flat top antenna situated above the building in which these racks are located. Now, the intended use of this amplifier was to be connected to the flat top antenna and that of a stationary ground, which effectively acts as a Earth to ionosphere receiving setup. But unfortunately, based off of some initial experiments conducted over the past month, the level of radio frequency interference caused by LED lights, nonlinear loads, and what have you, make it virtually impossible to receive the natural seismic activity which would otherwise be received by this amplifier, and likewise sent to other recording pieces of equipment such as the chart recorders shown on the rack. So this leads to a very extensive project which Eric and myself are working on currently, is how do we get around this sea of interference which basically plagues the vicinity of my operation. But nonetheless, despite the level of interference, the amplifier shown in the previous pictures will serve as a core piece of instrumentation to effectively utilize the principle of seismic forecasting. But also, eventually, this prototype amplifier will be held as a form of a commercialized, or I would say a saleable prototype design, which the experimenter may be interested in, but also for headphone application, it will be applicable to such degree. Now, Eric, if you want to add any other key points to this amplifier.
Well, the thing like you pointed out, the LEDs, from my observations with the equipment in my car, which is designed as kind of a sensory apparatus with the large antennas on it. This is getting worse with respect to time, and it's evident to me that the consumer LED light unit is actually a jamming device. And it puts out about as much radio frequency power as it does illuminating power. Very broad spectrum. It seems to focus very heavily on the AM broadcast band and the citizen radio band. And it's my belief that it's deliberate, and there's almost no getting away from it now. So I have a similar problem here, as there's a river of zero sequence harmonic current flowing into Earth through this part of the state of Nevada. It must be in the order of megavolt amperes, and it just completely trashed any possibility of receiving voice frequency signals out of the Earth, which was the primary objective of the project, which was devastating. So at any rate, to be evasive in the situation, what we're going to do here is we're going to make this more like the seismograph heterodyning device, and we're going to use a Tesla converter or chopper, and we're going to receive 30 cycles down to DC, which other researchers have found does provide advanced warning of seismic events. So basically that's what we're going to do here. We're going to go below 30 cycles and use choppers to bring it back up into the voice frequency so it can be audible. The amplifier, the one problem with the research of this, if we're going to get the right impedance transformers, the manufacturer will only sell 15 of them at a time. So basically every developmental amplifier that we put together, we have to sell enough of those to cover the cost of the transformers, which is rather steep. There's a large variety of amplifiers. Judging from comments I've received from people, what the public desires is a 100-watt bass guitar amplifier. There is a very novel Western Electric design that I can employ, but the initial cost of the transformers would be hundreds of dollars, and multiplying that by 15 makes that completely impractical. And the other thing is I don't really have a laboratory here such that I can build that stuff commercially. Now, the headphone amp, that's kind of a cheaper way. Here it occupies a significant portion of a rack of equipment. We can get this thing down into a fairly small package. And again, the problem is how do we get the transformers and where's the money going to come from to do that? So
I think we've already discussed.
Go ahead.
So the headphone amp, basically, I'm going to cover the cost of the production. It's going to be a consumer model that might be 6 inches, 7 inches cube, because it's going to be something comparable in form to the tube headphone amps you might find on Amazon or any audio company, and it'll be basically marketed to the average person out there, even though it might have more applications than just being a headphone amp. That's kind of the main thing, so that the average person out there can get their hands on something developed by EPD Labs that, preferably would be in at a reasonable cost. But it's my suggestion to just come out with a product and then just make profits that way to help take portions of those profits to help fund a lab, because donations are few and far between. I mean, there's steady, small donations, but like these big chunks are, just once in a great while. So if we have something to just generate the funds ourselves, at least that's something kind of within our control. Donations are not. And so as far as 15 units from Hammond, for these little headphone amps and that kind of stuff, that's easy enough for me to get that going. I just need the final design. I've seen some of the diagrams from Griffin and so forth, but once it's worked out to where what those specs are from Hammond and stuff, then we can move forward. So that's basically all I'm waiting for. I don't see it as really a big project.
Well, if you're willing to initiate that financially, then we're almost there.
Yeah, I've already agreed to do that. I just need, whenever you have the specs, to send to Hammond to get the quote and that kind of thing, to where we know exactly what the final schematic is going to be. Then it's just a matter of kind of laying it out on whatever kind of case. I got to get get the CAD design done for the case. Jeremiah here at the shop can help do that. Then we basically need a quote and a lead time. Cases for a small little run like that, it'll be 8 weeks. That's what I'm looking for the water machine.
So the amplifier, pretty much this initial version has been settled upon, but the power supply is still, Griffin's still got to hash that out. The regulator, DC regulator, the chokes, and so that's the only real engineering labor right now is the power supply. The amplifier, I think the last diagrams I sent to Griffin, I think we finally finalized on what transformers we want.
Right.
Audio transformers. But the power supply is still pending. But at one stage at a time, then the amplifier, without the power supply, that at least that could get started then.
Correct, because currently the amplifier is operating solely off of batteries to minimize any AC hum which may be present in the system. But of course, a designated power supply will not require any batteries should it be designed correctly so that it basically minimizes any hum.
Griffin, a technical question on the top of your rack there, where you've got the two presumably amplifiers, those two modules that sit on the front of the panel. Could you just say a little bit about what's inside each of those?
Which module are you speaking of? Here, I have the
yes,
cursor.
Away you have your mouse. Yes.
They're
Okay.
repeating coils.
Yeah, those just house the two coils which are connected to the.
Oh, okay, those are the coils. So they don't have the tubes inside them.
The repeating coils are they're a Bell telephone type thing.
Mhm.
Basically, they're kind of like 1-to-1 transformers
Mhm.
or 1-to-2 transformers, but they have very, very good phase characteristics because there may be on a long distance circuit, there could be 100 of these repeating coils in tandem.
Mhm.
So these particular ones are really only designed for either voice frequency or AM program service. But what's remarkable is even though they were never intended for high fidelity audio, this particular type of amplifier design makes them work as high fidelity audio because we're not using them so much as transformers as we're using them as chokes in a longitudinal coupling system. Because there's also a condenser that goes, or electrostatic condenser or capacitor that goes between the two transformers that matches or it tends to match. We haven't got it exactly worked out yet, but it brings the mutual induction of the transformers into the electrostatic mutual elastance of the capacitor and acts like a transmission network. So the transformers are actually components of a more complicated transmission network.
Mhm.
And where normally just one electrode of the tube connects to the transformer, in this a plurality of elements of the tube connect through the transformer in a manner that is not seen commercially. It's only been seen in wideband carrier telephone work. And I have designs up to 300 watts. I have a 5/8 watt prototype on the bench, which is probably the most novel amplifier that's ever been made. It does use a lot of transformers, but at any rate, it's got very good overload characteristics. It's got excellent fidelity. Frequency response is way beyond that of the transformers in use. And I would really like to scale that up into a 300 watt model that uses 811As. That's always been a dream of mine.
Mhm.
But that's kind of further down the line. So as far as the major attraction amplifier would be the particular Western Electric amplifier I was talking about that uses very novel circuitry. I think it would make an absolutely fantastic musician amplifier because it would have overload characteristics that have never been achieved in the amplifier designs that have, basically become established in the music industry, which are just repeat copies of 1920 designs. No one's come up with anything novel. They just, have a different package, but the guts inside, it's all the same RCA patent from the 1920s. Nothing's new. This is new, and I think it'd make one hell of a guitar amp. So I'm thinking that, as we move along here, that would be the main product. Instrument amplifier, musical instrument amplifiers. What you see in the rack right now is called an instrumentation amplifier, which is similar to the Steve McGreevy device in that its bandwidth and sensitivity and what have you is optimized towards instrumentation work, like Griffin was saying, was to convert from electrostatic to electromagnetic, so you're not drawing any current off of an elevated capacity antenna like the flat top.
And for example, what is the advantage there, for example, of using over something like something like a semiconductor amplifier that has very high impedance, like a FET input amplifier. What is the advantage, Eric?
Well, it's always best to stay away from semiconductors because they got funky characteristics.
Mm-hmm.
Vacuum tube characteristics are a lot better.
Mm-hmm.
Semiconductors are very prone to damage when you're doing electrostatic reception.
Mm-hmm.
Steve McGreevy uses the field effect transistors. His designs are quite successful. You know, I can have, when I drive over underneath the 1,000,000-volt DC power line for LA Water and Power, and have fire jumping off my antennas, and I accidentally left this box hooked up and did not burn it out. But people seem to favor vacuum tubes. Vacuum tubes intrinsically give better fidelity. The circuits are simpler. They work better with transformers, and that's what people want. And that's what, even though I have no aversion to using transistors where, you know, they're applicable, then there's no reason for using tubes. But the modern transistors in these chintzy little plastic cases and made in China and all that is nothing we build uses anything like that. And everything that's built that you've seen in these videos is all EMP proof. And I'm really insistent in not using any made in China techno junk anywhere in the system at all. So
very good.
That's kind of the philosophy.
Hey, Griffin, do you have any more slides?
Amen.
No, that pretty much covers the major stuff.
Okay. So if we could wrap up here in maybe about 5-6 minutes. Did you have a comment, Bruce?
No, well, I just said amen to Eric's comments because they were, you know, just music to my ears, Eric. Wonderful. Good going, old man. And to Justin, I wanted to say you've done superb work, and the achievements. I've sort of been out of the loop, and I didn't realize all this work was going on out there. I'll swing back to the early discussion on the coils. One thing I've done, and I've mentioned this in the signal network here, where we communicate back and forth a little bit. Please experiment with a primary driven coil, and maybe even with the Alexanderson coil. I'm not sure about that, but I've, you know, work with your spacing between the secondary and the primary. Now, I can achieve coupling and very efficient coupling, and I can't explain why, but very efficient coupling when my primary on a typical Tesla transformer is approximately the diameter of the secondary down below the secondary. And when I hook my vector analyzer on it, I cannot even see a coupling. It's not there. And from what I'm seeing, when I look at the spectrum, for Fourier spectrum analyzer, I'm seeing a single hump. I don't see a double hump resonance in the secondary. So, you have to get away from ferrite feeding these coils because it robs efficiency. And if you position your primary at a sweet spot, like I said, approximately one diameter down from the secondary, below the secondary, you will find 50 ohms, and you will eliminate the need for a coupler. You can directly feed the secondary, and with high efficiency. Adrian, maybe your analyzer, your vector analyzer could work better than the one I'm using, to figure out if there is a double hump resonance or not. But I'm not seeing it in the output. So maybe that's where you should expand your experimentation over Eric's ground connection out there at the lab. with the
It's definitely one of the
coils
to-dos.
you
It was just it was the engineering challenge of trying to get a coil that had a variable position on it. That was all. So, but it's definitely high on the priority list for the next set of experiments.
Okay, Hawkins, it's very good. I heard that. All right, well, that's really all I have to add. And I've been struggling with a lot of personal issues the last year, and I haven't had a lot of time to do anything at all. But hopefully, as the new year comes, I'll be getting back into doing some things, and do appreciate all the work you guys are doing. It's fantastic. My hat's off to you all. Thank you so much.
I am interested, Bruce, in how you get the power coupling between the primary and the secondary when you have such a large spacing between the two. I understand the impedance match, but like you, I don't understand the level of power coupling.
Well, all I can say is that I'm seeing output from the coil, whether I'm measuring neutral current or whether I'm seeing an arc discharge that is equal to or better than when it's close coupling. So so that those are sort of the metrics I'm looking at. I can't expand too much more in that direction, Adrian, but I encourage you all to play around.
I can. The important thing is that the resonant coil, or the Tesla coil, so to speak, be absolutely as free as possible to oscillate on its own. So any coupling to it lugs it down. So if you have a coil with a good magnification factor, you need hardly any coupling at all to get the thing to take off. It'll just suck the power. And the thing that we found here, particularly using these ferrite cores, is that the network analyzer just creates confusion. You have to go back to the old ways of doing things with more primitive equipment. So the method that I originally discovered this before I even knew about Tesla, with the laboratory I built with my equipment from RCA when I was in high school, is the other way, the series feed method, which I like. Again, you have to keep the coupling really low. So you need a really large mismatch between whatever the series feed element is and the Tesla transformer. So I used a Pi network, conventional Pi network with a massive output capacitor so that its reactance was negligible. So the coil was able to pretty much oscillate on its own, because the refraction, there was the refractive coefficient, so to speak, between the supply of energy from the transmitter and the coil was so tiny that the coil was able to take off on its own. But the magnetic loop, that's what we used on the Alexanderson coil, as you saw. And, we just kind of arbitrarily, what looked good, which was pretty close to the dimensions that you were talking about, and it matched up very well. And the coil operated quite effectively. The only thing I don't like about the loop is then that becomes like another tank circuit, but then sometimes you need that, particularly if you're using an oscillator rather than a master oscillator power amplifier arrangement, like Adrian uses self-oscillating circuits. Then it gets kind of complicated. But the important thing is that the resonant coil is free from being burdened by anything possible, including even a direct connection to ground. In Adrian's case, because he's using it for electrical discharges and not transmission. In fact, don't want transmission to get you in trouble. You don't need to ground the other side of the coil. You basically just connect it to a capacitance that is greater than the characteristic capacitance of the coil, which is something that's almost impossible to compute, but you can fudge it. So we basically used a metal workbench with the metal
ground plane
grounded, but it can go even smaller than that. In fact, I need to get your address, Adrian, so I can start sending you information on this stuff, because this stuff's going through my head all the time.
Sure.
And that's the easiest way to do it. And so you got diagrams and all that stuff.
Yeah, we'll look at it when we speak next, Eric.
Yeah.
That's fine.
Well, just have Griffin give me your address, and I'll start sending you information.
Okay, cool. Okay, that's good.
So that you can improve what you got. Because what I found is when you take the coil, the low end of the coil away from ground,
Mhm.
and connect it to some kind of capacitive counterpoise,
Mhm.
my experiments show that the smaller you make that counterpoise up to a certain point, the greater the magnification of the coil.
Mhm.
And in my initial experiments, I got the magnification so high that I couldn't even find it with the oscillator.
Sure. Look, I mean, Eric, in those terms, I mean, the most expedient way for those things to get me, if Griffin, you are willing, is Eric, you send it to Griffin, and Griffin can send it to me electronically.
Yeah.
Or I mean, you can send it to me directly if you want, but it's an international. It's an international post.
Yeah, I know. I'm doing that right now with Simon Davies on the music project.
Okay. All right, then that's fine.
That's the way I work. I like to stay away from the digital because writing is a lot different than pecking.
Sure, for sure.
And you get kind of more of your personality,
Yeah.
your ideas. You kind of have to think about things, and you read it over, and you go, "I better scratch that out. That'll piss them off."
Indeed.
But email, you pull the handle, and you're stuck.
Okay, that's fine. I'll give you my address, and then we can you can send me the materials directly.
It's not a hurry.
Yeah.
There's no reason to hurry.
I agree. All of the best things take time anyway.
Right.
The just a question, Eric, on what you were saying in the series feed mode. So, but when you feed on the series feed, as we say, how do you get the wavelengths to stack up? So we say, for example, if you look at the primary plus a secondary plus an extra coil, that we are trying to accomplish 3/4 or 3/4 of a wavelength or multiples. How do you do that with the series feed?
Well, then you just get one frequency. See, the whole thing is you have to reduce the number of modes as much as possible.
Mm-hmm.
So basically, you want to bring the resonant coil in the consonant resonance, so it only has one mode.
Mm-hmm.
And like when we experimented, we found when we used the push-pull, the two-phase coil,
yes,
is one half robbed the electrostatic potential from the other half.
Mm-hmm.
So it's the same thing with the modes, as they rob. And then when you start to have primaries and secondaries and all these, they all, as you know, they all add more modes, and that robs. So basically in the series mode, you can couple the series form, you can couple tightly into a particular mode and reject the other one.
Mm-hmm.
And have enough reflection at that point, so that the source of power is not lugging the coil down.
Oh.
But you had an initial point. You might want to repeat. What was it that you initially asked? Because
I was asking in the series feed how you get the ideal longitudinal wavelength to add up from what Tesla originally said. Because when you're working with a primary, a secondary, and an extra coil, then you can stack those things up across a single mode. You can do that quite accurately. But with how do you do that in a series feed?
You have a pi network to couple into it.
You have to use a pi network, huh?
Yeah, pi network.
Or a T.
Yeah.
Or a T network.
No, pi.
It has to be pi. Okay.
Yeah, because the thing is, you have to have the power factor correction. Mm-hmm. In other words, whatever residual inductance is in the resonant coil, mm-hmm. you have to have that amount of capacitance to counteract it. So there'll be an optimum capacity and there'll be an optimum impedance where the coil will really take off.
Yes.
But when you're using an oscillator, then that becomes problematic. So when you're using an oscillator, then you have to have some kind of tank circuit, and you have to have a coupling coil and what have you. So then you're kind of stuck unless you build an oscillator that has so much electromagnetic momentum this is the stuff that I'll send you. I've got a number of diagrams of what I did at the
Mhm,
Integratron. You build up so damn much electromagnetic momentum in what's the idler resonator that does not connect to anything.
Oh, that's nice. Yes.
So what you have is basically you have a flat spiral transformer.
Mhm.
It's got a massive primary loop. It's got an incredible magnification factor, very, very high current. In other words, very high magnetic potential.
Mhm.
And then you have another spiral inside that doesn't have any energy storage capacitor or any of that.
Mhm.
That goes to the tubes. But the electrical momentum of that big, heavy, so-called primary will make the oscillator stay on frequency.
Mhm.
It will
Yes.
override, and that way, then ideally, these things should be Hartley oscillators.
It gives it stability.
Yeah, and so you get the tap on the coil, and then like what Bruce Gavin was doing, then you take the resonating coil and you start to bring it in to this big, heavy-duty spiral, electromagnetic structure that's got, maybe. So here.
Yeah, go ahead, Eric.
Okay. Yeah, I guess
Just a little heads up.
But we're having such a good conversation, Aaron.
So at any rate, the important thing is, as you go down the line, is when you go from the resonant coil back, and Steinmetz showed the electromagnetic momentum should increase as you go further back down. Like that way, when you have a discharge, then the more
it reinforces.
Yeah, then it sends a traveling wave to the end of the resonant coil.
Yes, okay, that makes sense. Because then essentially the cavity in the core becomes coherent with the generator, and you end up with a completely coherent system, which is what we want to accomplish.
Yeah. Well, ultimately, you shouldn't use an oscillator at all. You should use a master oscillator and a power amplifier.
I like oscillators.
Well, because it's expedient.
Indeed, it's expedient.
But it has its problems in that you can't adjust the frequency to get the shape of discharge you want easy. With the master oscillator power amplifier, you can go to any extreme. And the other thing is it's not getting in trouble with the FCC or the military.
Indeed.
And it's a lot tighter in your country than it is in my country.
Well, we just won't turn the power up too high, huh?
Well, yeah, but we're going
or not keep it on too long.
Yeah, we're going towards the 40 kilowatt, push-pull triode unit.
Indeed. Yeah, I know. I am heading towards that.
I am intent on that, and
yeah. Well, that's why I need that transformer that's in your backyard.
Yeah, and you might even need to get three-phase power if you can.
I have three-phase power.
You do?
Yes.
Oh, then there's no reason to be screwing around.
Yeah, indeed. I will need that transformer in your backyard so we can get busy.
Well, yeah, you need a three-phase transformer.
Three of them.
Yeah. Or two in open delta. Two in open delta will work.
Yeah. Good.
But
work in progress.
The thing about three-phase, you don't need the choke and you don't need the filter capacitor.
Yes, indeed.
And you know how much of a cost and hassle that choke is.
Oh, indeed.
Yeah.
That's why I'm having to build my own.
Yeah, that's worse than the damn transformer.
Yeah.
So the thing is, I'm really intent on building this push-pull. What's the number of that tube? G5U or GU5?
The GU5B.
GU5B push-pull.
That I also want to build.
Yeah. Cathode driven by a pair of 4-400s. That would be an approximation of what I built in Bolinas.
Yeah.
And Aaron has a copy of what I built in Bolinas in a perfected form.
Oh, we need to see that.
Well, he's got it. Everybody's seen it. But the thing is we need the 40 kilowatts to make that thing take off and become supernatural.
You need a direct connection to the power line now.
Well, he's got three-phase power there, and the 40 kilowatts is peak envelope power.
Yeah.
So
indeed.
it means a 10 kilowatt continuous RF.
Yeah, a 10 kVA should do it. That's the
Yeah,
transformer that I'm using here in the UK is a 10 kVA.
Basically, the setup that he's got now, the next stage would be the iMac Tetros, which would be the 4-400s.
Yep.
In this case, we're using 4-250s because that's all, that was available at the time and what have you. And then that cathode drives the big tubes, which
Yes,
would be
indeed.
another
The
piece of
GU5Bs, yeah, a pair of GU5Bs.
So
we
now-
have to
now-
build that amplifier.
Yeah, well, I'm
sure.
intent on building it, and it'll at least be 6 feet of rack.
Indeed.
And,
That's the one I want to build as well.
Yeah.
And we'll get started on it.
So basically, it's the 4-400 pair is the input amplifier,
Yep.
and GU5B is the output amplifier.
Yep.
And I have a number of variable frequency oscillators, but that stuff, you can use China boxes or what have you.
Yeah.
And get it up to the drive point for the 4-400s. Now, the main problem with cathode drive is the filaments are hot. And that creates a complication in how do you isolate the RF from the filament
But
transformer.
you can get very high efficiency in that. Cathode drive, you can get very high. We can get it
I
very
know.
highly efficient.
Yeah, I know. And very good
More
stability.
than 90%.
Yeah, those tubes are, I think when you were there, I estimated by looking at the tube charts is that they're capable of 20 kilowatts peak envelope power
Yeah, I agree. They are.
each.
Yes, each.
Push
Yes.
pull pair would be, and here's the disturbing thing of, everybody else is doing all this stuff. And flailing, so to speak, because you can't afford it, or you don't have this, you don't have the power, what have you. I have a pair of 5 kW AM radio transmitters sitting here, and I can't get the money to hook them up.
Yep.
And as a last ditch effort, I have 3.
We're not going to stop, Aaron. We're not going to stop.
Yeah. Well, I'm wrapping it up. So the thing is, I got to get something in Aaron's rack that's preformed. The
Yep.
hard part's all built. The power
Yep.
supplies, the modulators, you've seen it. That's all the hard part.
Yep. Yep.
So I think which you can verify that hard might not even
We're going to
be-
show that next live call in the Colorado Springs
Yeah, so-
presentation.
So basically, the objective is in the next work episode here is going to be concentrating towards the inside of the building to try to at least, start to make some plans to get some electricity, to get some stuff hooked up, to get outlets and
Yeah.
that kind of stuff. Is these 3 1-kilowatt amplifiers, we're going to take steps to get those going. So
Good.
one is for Aaron, one's for here, and one's for Griffin. So for here, we're going to get an experimental FCC license, and we're going to, the 2.3 megacycle or what have you, we're going to put a Morse code beacon station in. That's the next step. Griffin, for his purposes or whatever he builds, he needs the power amp too.
Mhm.
And then Aaron needs one. Aaron's already in the RF bay, all the necessary bias voltages, everything's all there to run this amplifier. So it's rack mount, it'll fit in there, and it'll be an expedient. And plus, I have a number of HF oscillators out of the RCA receivers, spares. And what's nice about these setups is they have AFC, so you can, the master oscillator can lock into the discharge.
Mhm. Yeah, that's needed. That's critically important.
Driven AFC, so I've got more than I need for the receivers. So basically, there's enough stuff here that if I could keep everybody here on a constant basis, they'd be busy all day.
Indeed, I agree. We have much to do and not too much time to do it.
Stuff here.
Yes.
This is standard surplus.
Yep, absolutely. We need
Okay,
a
I
benefactor.
guess-
We need it soon. Aaron, I'd just like to add one more thing. Is that if we could please kick off the next live call that we do with the Colorado Springs, because we have a lot to present there. And also, I have quite a bit to present also in terms of updates on the golden ratio work and stuff like that. But let's leave that to
Sure.
another time.
Okay. And one thing I was thinking while Eric was describing to you that setup is that, you know, between the public calls with all the questions and that kind of stuff, we could always set up a live Zoom call where Eric can get on there and we can just record like, you know, 45 minutes or, you know, something like that of discussion and just put it up where we don't need to take questions and stuff. So we could do those too.
Sure, because that could that could drill into the specialist things, which will be interesting to those people that want to drill down to the details.
Right.
Yeah, that might be a good way to do it. Like what we did, what was it, about a month ago?
Yes. Yes, indeed.
Yeah, that would be a good way to do it.
Yeah.
So 4 weeks from now is January 20th, Saturday. Does that look like a good time to do the next one? Same time, 1 p.m. Pacific?
That would be good with me. Eric?
That good with you, Eric?
Any day's good for me. I
Okay.
have no, any day's good
Should
for
be
me.
good.
I could do this every day.
Yeah.
That would be a lot of recording for Aaron.
Right. Well, this video I might not edit. I might just put subtitles of the websites and then just, you know.
You know what,
upload it.
Aaron? That will save you a lot of time. I think it will be just fine like
Sure.
that.
Yeah. Okay, so everybody make sure to, you know, go to Amazon, get your copy of Nikola Tesla Polyphase Power by Eric Dollard. You can just search Dollard and Polyphase on Amazon and this should come up. If you want the ebook instant download, that's on emediapress.com. I just wanted to show something real quick here. Let me do a screen sharing real fast. Where's that at? So Eric was talking about musical seismograph. That'll come up here in a second. So you can go to emediapress.com. And then in the search bar at the top right, you can just type in the word musical and this presentation right here will come up. You can just click on it and it'll take you to the full page description. That's a musical seismograph where they're in the mine. It's actually kind of a compilation of probably about 5 different presentations all in one. And then this electrodynamic seismic forecasting is also going into some of the same topics. And then I just wanted to show, let's see, there's a couple YouTube channels here. If I can move this Zoom thing out of my way. Let's see. So my YouTube channel is basically youtube.com/Aaron Murakami. If you just type my name in there, you'll find it. This one right here was put out about 2 months ago. This is some after conference experiments we did here in the shop here in Spokane after the conference towards the end of July. Adrian did a 4-hour presentation on this. This shows some extra experiments. I'm sure Adrian, you know, and Eric can go more into this on the next call.
Sure.
And but you can watch this on the YouTube channel. It's 51 minutes. And then the next one, this was put out.
Aaron, I would suggest that we do that after the Colorado Springs. So maybe in a subsequent live call, because there's so much to cover in the Colorado Springs presentation.
Sure. Okay. And then the Colorado Springs one, this was put out about a month ago. And this is 1 hour, 41 minutes. So this has quite a bit. It's got some pretty astounding audio demonstrations with the flame, you know, the different variations of the flame speaker. So we can go into this on the next call, but if you all watch, at least go and watch this first, because then when we get onto the call, you know, you might have some questions, and I'm sure, you know, Eric and Adrian will address a lot of the stuff that you might be wondering about this. But for the full length presentations, those are on emediapress.com as well. You can just look up Colorado Springs, golden ratio, you know, those 4-hour presentations will come up. And so,
but also,
and then
Aaron,
again,
would you also mention my YouTube channel? Because I have many of these also on my YouTube channel as well. People could go to.
Yeah. What is the name of your channel? I guess they could type in Adrian Martian. It'll come up, or
they just type in AM Innovations.
AM
Innovations. All just in one word. Yeah.
So scroll down. Yeah, you'll see it right here with the AMI in gold in a
AMI,
black circle.
that's the one. Yes. If you click
Logo.
there.
Yeah. So AM Innovations.
They've got many of the videos and things that we're talking about and stuff like that is mirrored also with eMedia Press as well, Aaron.
And then I'll put everybody's websites as subtitles and stuff in the video that'll go on YouTube. I'll get to that as soon as I can. And then again, you know, as Justin was saying, and, you know, Adrian was emphasizing, you know, all the support and everything. If we had a benefactor who could, you know, present, you know, help with a lot of the funding to take it to the, you know, multiple, you know, different orders of magnitude above where we're operating at right now. But in any case, you know, go to ericpdollar.com, hit the donate button. And if you can donate by PayPal, send a check or money order, you can see that, you know, all these donations obviously goes to exactly where it's supposed to. And that is furthering the, you know, science and furthering the research in the electrical sciences. And there's a lot of groundbreaking stuff that's going on right here with this collective group. That's not really happening anywhere else in the world. And if it is, nobody's talking about it, but we are, you know, showing it, we're sharing it. And so please spread the word. And until next time, we'll see you again. And hey, Merry Christmas, everybody. Happy New Year's, whatever you happen to celebrate. And we'll talk to y'all next year.
Merry Christmas. Thank you, Aaron.
And Merry
Hey,
Christmas.
take care, everybody.
Pleasure.